Hello, welcome back to Quantum Computation Simplified Part 10. So in this video, we will see how to solve linear equations with the help of a quantum computer or a simulator. I'm sure most of you are familiar with the system of linear equations. In general, it is represented by Ax equal to b, where A is a matrix of coefficients, x is a vector of unknowns. That's what we will be solving it. And b is the vector of solutions. Okay, so in order to understand it better, let's take an example. So this is a set of simultaneous equations with two variables x1 and x2. So 2x1 plus x2 equal to 5 and minus x1 plus x2 equal to 5, and this can be solved by representing in ax equal to b form. So let's take the coefficients and put it in A matrix 2 1 minus 1 1. Then you have the vector x1 and x2, the unknowns, and the vector is made with the help of the numbers on the right side of the equations, that is 5 and 2. So now we have A and B, and we are supposed to get the values of x1 and x2. In fact, for this such a simple one, we don't need a quantum computer or any classical computer. We can do it manually, right? So if I subtract this equation from here, then it will become 2x1 minus of minus x1, that is 3x1, plus x2 minus x2, so x2 goes to 0. That term goes to 0, then 5 minus 2, which is 3. So 3x1 equal to 3, so x1 equal to 1. And when you substitute x1 here, you will get x2 as 3. So it's simple as long as there are the number of variables are less, like in this case only 2, but it becomes very difficult when the size goes up. And today, with a lot of data available, the equations are growing very rapidly over time. And you can see such requirement in many branches of science and engineering, even in economics, mathematics, right? So electrical circuits, networks, heat transfer, statics and dynamics, every CFD package, CFD and FEM package uses this kind of, they try to solve this kind of problems. Chemistry, economics, linear programming, games, AI, ML, like that, it has got plenty of applications. So if you are able to develop a good algorithm using quantum computer, then it will be of great help to the society plus for your own problems, right? And typically we try to solve by many ways, like substitution method, graphical method, matrix, Cramer's rule, Gaussian elimination. And some of these methods are good even to handle larger matrices. Then you may wonder, why do you need a quantum computer to solve this? So that is explained in these two bullets. So typically a classical algorithm runs with capital O or n into k, where n is the number of variables, right? It determines the size of the matrix what we are talking about. And k is the condition number. So what is condition number? You can Google it, but generally it will be much lower compared to the size of matrix or the size of unknowns. Okay, whereas the quantum algorithm runs with O log n k square. In fact, they depend on a couple of more variables like sparsity and then the error what we are looking for. But for simplicity, I just used only these two variables. And the most important thing I want to convey here is, so this is a function of n, whereas quantum algorithm is a function of log n. So you know the benefit. We are able to do it with much less number of steps, right? And there are in fact many conditions for using this algorithm, the one what we are going to see, HHL algorithm. And the most important thing is the matrix A should be a Hermitian matrix. So what is that? We will see it later. So before proceeding further, actually in order to understand the video, you need some basic knowledge of quantum computing. So I would request you to see my previous videos, part 1 to 6, or you can see any other video or read textbooks in order to understand this video. You also should have some basic matrix knowledge like inverse, eigenvectors, eigenvalues, and Hermitian. So Hermitian is, of course, it has got a lot of properties, Hermitian matrix. The one what we are going to use effectively, for our application is a matrix is Hermitian when it's equal to its own conjugate transpose. Okay. And it's desirable if you are good in linear algebra with more knowledge about decomposition of a matrix and things like that. And a little bit about quantum mechanics on what is Hamiltonian and then how do you evaluate computer algorithms and that. If it's not, that's where we use to capital O N, right? In order to understand this, knowledge in these areas will be helpful. But if it is not there, it's okay. I try to put the minimum essential things to give you the gist of algorithm. Okay. And before really going to the algorithm, we will see some of these mathematical steps which are used in the algorithm. The first and foremost, we know that so we are trying to use, we can solve Ax equal to b by taking A inverse x is equal to A inverse b. But how do we do it in a quantum computer? So that is what the algorithm gives the steps. But fundamentally, you are aware that everything we represent in terms of states of qubits, right? So we have to represent like this A state, ket x, you know that, is equal to ket b. The algorithm takes state b and then it does some operations and gives the value of x. And how many qubits are required typically? To represent b, you need log n qubits. Assuming that to the base 2 for b. Depending on the size of b. Suppose you have two states, you need only one qubit. If you have 4, you need 2 qubits. Suppose if you have 3, you may have 2 qubits, and then you have to do a little bit modification to make use of the algorithm. Matrix may not be a unitary matrix. That is the most of the time it will not be a unitary matrix. You know that not every matrix is a unitary matrix, and we have also seen what is a unitary matrix. So every gate should be represented in a unitary matrix in quantum computer. But if A is Hermitian, then e to the power of iat is unitary. So that is one information which is very useful, and that is being used in this algorithm, and that can be represented by this ket uj. This is eigenvector, and this we know that bra, this is like a row vector and column vector, and you know that this is outer product multiplied by e to the power of I lambda t. Okay, what is lambda? Is the eigenvalue, and if the matrix size is like a matrix size is n by n, then you will have n number of eigenvectors and eigenvalues. So that is what is given here. A itself can be represented. So this is what is the matrix decomposition, what I was talking a few seconds back. And once you are able to represent this way, then getting A inverse is very simple. You just take inverse of the eigenvalue. You will be able to get the A inverse. And we said in the previous slide that A should be Hermitian, right? In case A is not Hermitian, what you can do is you define one more matrix C, and then use A, position it like this, A, and this is its conjugate transport, A dagger we call it, right? And then you define one more equation, Cy equal to B0. And what is Y? Y is 0 and X. right? Like this. I mean, you can, they're all vectors. So once you are able to solve y, then from y you will be able to get x. And when you are starting, you have to express the vector b, the given vector b, first in terms of qubit, and later during the process we'll be able to represent as a linear combination of eigenvectors of a matrix. You know that, I mean, we have seen it earlier, that any matrix, sorry, any vector can be represented as a linear combination of other vectors within that same space, right? Phase estimation algorithm lets us find the eigenvalues of unitary matrix using quantum Fourier transform. So this we have seen it in one of our lectures, source algorithm, wherein we try to find the period, I mean, right, to using QFT. So, and then in this case, okay, from the period we are interested in the eigenvalue. So anyway, the detail will be coming later in this video. Another important one, actually, I mean, if you don't understand it fully, it's okay. But I need to bring it because some of the papers, they refer one of the operations as Hamiltonian simulation. So that's the reason I'll touch upon that. You know that the state of quantum elements or a quantum system, it's represented by a Schrodinger equation. So this equation is for an element, right? So typically it gives the relationship, and using this we will be able to evaluate the wave function, which basically represents the position and the momentum, and we can evaluate once we know the energy of the system. So, and plus the initial values. So it's typically like a single order differential equation, and that is given by another expression like this: the state of this is okay psi, the what do you say, the wave function with respect to time t is given as exponent minus I h t. H is the Hamiltonian representing the energy of the system or the quantum element, times again the initial state. Okay, and generally what happens, it will go and settle down as we apply energy at the eigenvalue of this guy. So that is what is a Hamiltonian simulation. That is, you set the parameters and allow the quantum elements, in our case qubits, it will go and nicely settle at the initial state times the eigenvalue. So once, I mean, from there we can extract the eigenvalue. So I'm sorry if it is not fully understood, it's okay. And then, I mean, as we go through the algorithm, you will be able to catch up something. Even if it is not there, then no issues. We will see how. So yeah, the crux of the problem, the crux of this video is HHL algorithm used for solving linear equations. So it's called HHL. It's given by three scientists: Harrow, Hasidem, and Lloyd. Okay. And they have given the algorithm in three steps or three subroutines. They call it as phase estimation, which is used for finding out the eigenvalue. Then R rotation to get the value of the inverse of eigenvalue. Then we have to do some uncomputation as a new terminology. So how that is done is, let's start with the input B register. So we know how from the B set of values we have to represent in qubits. Then we will use a set of clock registers. So all the qubits in this register will be set at zero state, and the number of qubits what we use will be based on the accuracy what we are interested in the result. And similarly, the number of qubits we have seen earlier, that log n to the base of 2, so that many qubits will be using. and the ancillary register, that is actually it will help us to do some operation. Okay, so we have to have ancillary register also set at the 0 state. So what we do, so we'll take the B and then you apply U gate. So this is nothing but e power IAT. Okay, that you apply on the result of register, from the state, the 0 state, you apply Hadamard gate, then on that state you will apply e power IIT. So then we will get here itself the phase or eigenvalue in Fourier basis. So we need to do inverse Fourier transform to get in our measurement basis, that is in zeros and ones you will get it. Then using the ancilla and using this OR gate, we will be able to get the inverse. So what is the use of this? Okay, so what we need to get is first the answer, and second thing is in case, and we'll also be looking at what is the output at this ancillary register. So if you are not getting as 1, then we need to repeat the whole process. You know, repeating is called amplitude amplification. That we have seen it in Grover's algorithm, right? So similar step we may have to do it. So in that case, what happened? We started with 0. Now what happened? These two registers will be entangled, and also it will have some junk value, right? So if when we want to repeat, it should go back to its 0 state. So we are doing this for two purposes. One, to disentangle them or break the entanglement. Other one is to take these registers back to its original value, that is 0. So that is achieved by Fourier transform, U dagger, and then Hadamard gate. So though it looks very simple, but practically you need to have a lot of gates. Even as an example, the U gate, e power IAT itself, you can see it is represented with so many other gates. And again, this is for a specific application. It cannot be standardized or universalized. Okay. So that's the reason actually I'm not going into the detail of each and every gate, though it looks single gate, so it will have its own sub gates, or it can be broken down into many gates. And the reason why I'm not going into the detail is, if you're strong, and certainly, yeah, I'll come back with much more detail. But without knowing that, also we'll be able to solve, the linear equation. So that is the reason I didn't go. And we also need to understand some of the libraries already available, and it's all given by, all the people who are hosting the quantum computer. So in our case also we will try to see how to solve linear equation without really understanding each and every gate by using the functions given by IBM. So let's take a sample problem. 1 minus 1 by 3 minus 1 by 3 1. So this is Hermitian, right? And then b equal to 1 0. So, and then yeah, manually if you try to compute, you will get x1 equal to 9 by 8 and x2 equal to 3 by 8. Okay, so let's go to IBM QISKIT. Yeah, so this is a program given by IBM, and I try to remove certain things so that we don't spend much time. So we need to import the functions already available. Some of the library functions you are familiar, like the first one. The second one is a new one, basically for doing QFT directly. And the important things are these two actually, HHL, which will, this is the core algorithm which is written and then given to us as a class. Okay, so then eigenvalue using quantum phase estimation. There is one thing called lookup rotation for inverting the lambda. Okay, and there are a couple of other functions we will see as we go through. In the meantime, I'll also just run it. So first we are declaring the functions, and this is the function which we are writing actually, right? And this function doesn't do great work. It just calls another inbuilt function. So while calling our function, we need to give the matrix and number of answer bits what we want to use, and the time slices, which is not very clear about this, but I only guess that it's like our step size, okay, in integration. And then this is very important, we need to say whether any of the eigenvalues can be negative or not. So but if you have doubt, you better say yes. And then what it does is we need to increase the ancilla bit by 1, and then we have to modify the circuit little bit. So that is what is being done once we say it is true, okay. Then we are calling the existing function given by IBM. So wherein we try to call the matrix operator. So I mean that fundamentally, if it is not a Hermitian, we need to do something more, right? We have seen we'll define one more matrix. So those operations also can be done by the functions available. Then you call QFT. I mean, in fact, inverse QFT. And then time slices we have seen, and number of Angela bits, and then there are a couple of algorithms available. You can choose which one you want to have, and within that algorithm what is the order. So I mean, my suggestion is you go with the default one, and then once you have the feel of it, you can change the algorithm and change the order and see what happens. So if you don't know the evaluation time, the end time, you know that like we have seen the Hermitian, I'm sorry, uh, simulation of qubits, right? So it will go and settle after some time. If you know the time it takes, you can specify it. Otherwise, you can leave it as none. So they will try to do it in an optimum way. In case you are not happy with the result, you can increase the time and see what happens. Okay, and then negative eigenvalues there or not about the then the circuit. Should you need to modify for negative evaluation or not? That is what we are giving as the input. Okay, then yeah, this is where we are defining the problem. Like we have seen the matrix A is represented like 1 minus 1 by 3 minus 1 by 3 1, and the vector B is represented as 1 0. Now we are going to call the functions original, I mean the size is the length of the vector, and then as I told you, should you need to truncate or not in case the A matrix was not Hermitian. So that is what is being done here. Then eigenvalue, we are trying to call the function what we declared earlier, the matrix and the number of ancilla bits, the time slice, and then there is no negative eigenvalue. And then it also gives us how many qubits used, and how many ancilla qubits used also. Then you initialize particularly the B vector, and that is what is being done with this function, again given by IBM. Then we have also seen this function declared earlier, given again by IBM. This is to reciprocate or invert the eigen value. After that, we are creating one instant for HHL, which we are interested in, right? And later we will execute this algo, okay? And this is another simple function for fidelity, just to compare the result what we get from a quantum simulator and in a conventional way from NumPy. So that is, it's, I mean, just to compare, right? And then here we are executing in a quantum simulator algo.run, and then we are also executing using NumPy solver by giving the same matrix and the vector. Then here we are trying to compare. So let me run this, okay. And then let us see what we get here. So Yeah, you know that. So this indicates that it is being run. All right, we got a solution. You know the classical solution, we have seen it earlier, 9 by 8 or 1.125, and this is 3 by 8 or 0.375. So our solution is close to the actuals, but not exactly. And if you're not happy, we can repeat, but now we are not going to do that. The fidelity is calculated as 0.99432. You can try to improve further. It depends on the application. In some cases, we may not be interested to increase, but in many cases, we'll be interested to get the exact value. So we need to do the amplitude amplification, right? And this is another interesting step actually. So there is something called circuit width and circuit depth. So width is nothing but the number of qubits used. Depth is nothing but the number of gates used, and out of which there are 54 C0 gates. So you will get roughly whether we can do it in the actual quantum computer or not, because when you want to have 54 C0 gates, you know that typically a C0 gate can be implemented provided the two qubits, both control and target, they should be adjacent to each other. It should be possible to connect them, right? So that makes things very complicated, and that's the reason we are not really successful in solving big matrices. You can see even with the two elements, it's going to be tough. But the interesting part is this algorithm will work even when the matrix size is 1000. So that is the purpose we people, I mean, the big companies, they want us to learn quantum computing, try to come out with the fantastic algorithms so that once the hardware, the quantum computer hardware is available, these algorithms will help us a lot. So don't worry that we are unable to use a quantum computer, but certainly we should prepare ourselves and then ready for using it. Okay, that's all I have technically, but let us see the references what I used. So as usual, the QISKIT documentation is extremely good. You will understand better there. I mean, then there's another paper which also, I mean, you get some idea. Unfortunately, I mean, you need to read again and again to get a better idea. I try to simplify and try to remove the confusing factor. That's, I mean, but certainly that is not the right thing to learn. We need to really go to the fundamentals. Wikipedia page is there. As usual, you get some knowledge, but unfortunately, this is not that elaborate to understand this particular algorithm or the way how to solve the equation. And there is an excellent video also available. And interestingly, this video was made by one of the authors of HHL algorithm. Okay. And there are many more papers available, and this is the original paper by the three authors HHL. And there's a nice paper by Datta et al. And then they taken another problem and try to explain step by step. And they have the reference from this paper. So this is again a great paper. You will get some idea about the searches algorithm in slightly maybe better way. And as usual, we have this Bible of quantum computing. Unfortunately, there is no separate chapter on HHL algorithm or solving linear system. But certainly, you know that this problem is broken down into many subprograms, and all those sub-elements are all nicely covered in this textbook. So what next? I think it's a time for us to go back to the basics of quantum computing, then including linear algebra, I would say. Then I think I'm also going to do that. You can also try to do that. Let's start coding, and then try to see what happens by changing some of the gates as we learn. And I'll do that as I told you, and then come back to you with some more videos on basics, so that we'll be able to write our algorithm soon. So till then, bye, and thank you for watching this video.